Lines are connected horizontally to all the memory cells in that row. Upon activation of the word line, all the memory cells in that row will be turned on, activated, and then bit line will read the value of the cells or will write new value into the cell. Once again, what is the definition of memory cell? It is the intersection of a word line and bit line. That's we get a memory cell. Now, at that intersection, presence or an absence of a semiconductor device will give us one ROM cell or zero ROM cell. We are talking about binary memory. And we are talking about permanent storage. So some of the cell will permanently store 1, some of the cell will permanently store 0. So two types of ROM cells in terms of their information stored. One is binary 1 or binary 0 cell. Now, and each cell is the intersection of a bit line and word line. At the intersection, sometime presence of a semiconductor device will give a 1, sometime absence of a semiconductor device will give a 1, and sometimes it's opposite. Presence of a device will give a 0 or absence of a device will give a 0. It depends on how we connect it. So first look at the diode ROM. The first one is called one cell. At the intersection, there is a diode connected. By the way, word line and bit line, they just pass over each other. They do not touch each one of them. Electrically, they are isolated. Word line runs this way, bit line runs this way. But at their intersection, at their passing over, it's insulated from each other. They do not electrically touch each other. So there is no junction connection, electrical connection in any of this intersection. Connections will be there only when it is designated by a circle. That circle means there is an electrical connection established. So for diode ROM, a diode is connected from word line towards bit line. So it will be forward biased in this direction. Diode can only carry current in one direction, not the other way, right? So it will be this side to this side. And in zero bit ROM cell, based on diode design, there is no diode. So in diode ROM, presence of a diode at the intersection connecting word line with the bit line means one cell, absence of a diode means 0 cell. First, absorb that information. Presence of a diode at the intersection gives a 1 cell, absence of a diode at the intersection gives a 0 cell. And the intersection itself is a cell. Now the question is how it gives us 1, how it gives us 0. Because it's a ROM cell, every time we read this one, bit line will produce a 1. Every time we read this one, bit line will produce a 0. How do we achieve that? First thing we have to remember, in diode ROM, bit line is by default connected to ground. Bit lines are by default on one side, this side or this side connected to ground, and signal is read from the other side. So the bit line will have two sides, either this side or this side will be connected to ground, and output, signal output is read from the other end of the bit line, which is connected to the output of the memory circuit. So now, in this case, every time you are reading a ROM cell or any memory cell, you have to activate that memory word. How do we activate that? By turning on word line. By connecting it to supply. When I connect this one to supply, the value of word line becomes high. In this case, when you connect positive signal, high signal to the P side of the diode, it gets forward biased. Diode becomes short. An electrical connection will be established from word line to beat line. Beat line is by default at 0. Word line is now activated by connecting it to the supply. So the diode is forward biased. So it will inject voltage from here to here because it is high, it is low. Right? So beat line is default at ground. So beat line will experience an upward charging. And there is a sense amplifier sitting there which will see is beat line going up or down. Default it was 0. Now beat line says that it is going up. It will never go, the way it is designed, it will never go up all the way to VDD. Sense amplifier, all its need, is it going for 10 to 20% of time, continuous up? The moment you activate the word line, diode is forward biased, a connection is established, this is powered, this is grounded. So charge will be injected, so beat line will go up, sense amplifier will sense that it is going up, so if this side is grounded, the other side will deliver a high signal, that means output will read a 1. Since this diode is permanently connected between word and beat line this way, and this beat line is permanently grounded, we activate and deactivate this word line. So every time we activate the word line, beat line will see an upward charging. Every time the sense amplifier will read a 1. Beat line will deliver a 1 to the outside, so it is a permanently hardwired 1. On the other hand, here, beat line will start reading only when word line is activated. Control circuitry will control that. It is synchronized. Upon activation of the word line, there is no electrical connection. No change will take place in the beat line. It will stay at its default ground value. So the sense amplifier and the output circuit will read what? 0. So the default 0 will be read or delivered to the outside. So it is a permanent 0. So it's the simplest possible design you can have. Just one diode. Absence and presence of a diode is giving us 1 and 0. However, it has a disadvantage. Disadvantage is that word line, one word line, is connected to many beat lines, and that vertical beat line is passing through many word lines, right? So depending on signal combination you're storing, there may be many diodes connected to this beat line. So if that beat line, that vertical beat line, will have many parasitic capacitance connected to it, contributed by all the devices that are connected. So every time you activate the word line, it is becoming short circuit with that beat line because diode is on in forward bias direction. So while you are trying to charge up the word line, it will charge up all the parasitic capacitances that is connected to the beat line. So it will unnecessarily consume power out of the word line supply, and also the signal transition will be very slow because all the parasitic capacitances connected with the beat line will need to be filled as it is going up. So the transition will be very slow because charges will be taken out by all the parasitic capacitance in other word line which is not supposed to be on. This is happening why? There is no, when it is activated, there is no electrical isolation between word line and beat line. They are electrically shorted. So all the capacitance here and here will be charged by the supply connected to the word line, it will consume unnecessary X amount of power, and it will make overall operation very slow. That's why, although it is the simplest possible design you can have in any memory design, still it is not recommended because of the power consumption and slower speed. So how can we mimic the same operation using a MOSFET? Exact same thing. At the intersection, presence of a MOSFET NMOS transistor will give us a 1 ROM, absence will give us a 0 ROM. This will be identical. There is nothing to explain. Bit line is by default connected to ground. When I activate the word line, no change is taking place in the bit line, so at the output and the sense amplifier will read a 0, right? Because bit line is default connected to ground. But what happens here? First, let us explain the connection. This NMOS transistor, one side is connected to bit line. The word line is acting as the input to that transistor, and other side is connected to VDD. Now, word line is the input to all the NMOS transistor in that row. Good thing is, when it is connected to the input, it is completely insulated from this connection, because gate terminal is insulated from the drain and the source. So, only thing word line supply has to do, just turn on a single transistor, and then the other side of the transistor is connected to VDD. It will charge the bit line upward for the sense amplifier to sense that it is going up and deliver a 1 to the outside. So here, it is the word line is responsible for charging up the bit line. While it is charging up all the parasitic capacitance. Here, this entire bit line and the word line, they are electrically isolated from each other. Word line switching is not delayed by any parasitics connected to bit line, because its only job is to just apply the input to the gate, which is insulated from the transistor, main body, source and drain, and this bit line is connected only to this transistor. And this transistor will inject charge into bit line. Although it's an NMOS transistor, we don't care. It is a good pull up or pull down device, because sense amplifier only need to see whether it's going up or down. It doesn't need to wait all the way to VDD, right? So as soon as this transistor is on, VDD will start charging bit line. Sense amplifier will see that it is going up, and it will produce a 1 to the outside world. So identical operation. The advantage this one is giving us, complete electrical isolation between bit line and word line. This is another disadvantage. Memory circuits are operated at a very low voltage swing. Sense amplifier will amplify it. So if a noise injected accidentally to the word line during the operation, because it is short, it will disturb your bit line. While it is going up, if the noise is negative, bit line will see a dip instead of rise, right? So it may inadvertently read a wrong signal, because electrically they are short. But here, electrically they are isolated by the gate, so after it goes up, if any noise affects here, it will be isolated from the bit line, because the word line is delivering the input to the gate terminal of the NMOS transistor. So this is presence of an NMOS at the intersection gives 1, absence at the intersection. So in both cases, bit line is by default connected to ground. Sense amplifier will see whether it is going up or down. In this case, it will see that it is going up, so it will interpret it as 1. In this case, nothing will happen, remain at default ground value, it will interpret it 0 every time you activate it. The only disadvantage of this one, NMOS takes significantly more area than a diode, because it has to have this connection, and then a VDD line must be routed parallel to the word line. So that additional circuit resources. So between every pair of word line, you have to route a VDD line. So additional circuit resource overhead for running this VDD line and then additional connection for NMOS transistor will consume more area and circuit resource compared to diode ROM, but it will be more robust and higher speed in terms of diode ROM. Now, IC designers, they always look for alternative. Well, here bit line is default connected to ground. What if we connect bit line default to supply? And I want to implement another version of MOSFET. In this case, here bit line is default connected to VDD. This is different. On one side, other side is sense amplifier and the output is connected. Here, absence of any device means 1. Why? When you activate the word line, there is no connection. Word line will not affect bit line. Bit line is by default connected to supply. So every time word line is activated, sense amplifier and the output will read the default 1. So nothing needs to happen. It will deliver 1. But here, as you can see, transistor connection is switched. Top side is connected to bit line, bottom side is connected to ground. It doesn't matter. I can connect it to bit line, connect it to ground, right? One side is connected to ground, other side is connected to bit line. Input again is connected to word line. Default value here, bit line is connected to supply. These two default bit lines are connected to ground. So what happened? Upon activation of the word line, the transistor is on, bit line gets connected to ground. The default value of bit line is high because it's connected to supply. The moment it connects it to ground, the bit line will start discharging. It may not get discharged all the way to 0, but sense amplifier will see that, well, initially it was default high. The moment the transistor is on, it is connected to ground, so it is going down. Sense amplifier amplify that, and it will produce a 0 for the output. So here, absence of an NMOS transistor at the intersection gives a 1 ROM. Presence of an NMOS transistor at the intersection gives us a 0 ROM. Only thing we have to remember, here default value is 0, here default value is 1. So these are the 3 different types of ROM we have explained. So we have already explained the disadvantage of diode ROM side by side. So second one, that's what I'm talking about, alternative. So now the question is, let us now talk about these two. So this is hardly used because of all the disadvantages we talked about. Short circuiting, noise problem, higher power consumption, and slower speed. We use these two, one of these two in your design. Since ROM are permanent one-time design, and you know what set of binary bits you want to store, because it's hardware design for permanent set of information at the time of manufacturing. You never change during the lifetime of this computer, right? So since you know that what binary information you have to store permanently in that ROM, so you as the designer will select one of these two. Can anyone elaborate which one you would select?
2.
Based on what?
Well, won't your collection logic also use a MOSFET that will end up inverting your output signal?
No, it is the same thing because operation-wise, complexity-wise, same, exactly same complexity. The absence and presence that's use that logic. if you know, first of all, as a designer, you want to implement your design with less number of transistors.
Then the
If
ROM
you know
1.
that the bit sequence you want to store that has less zeros, more ones, I'll go with this one.
Less zeros, more
Makes
ones.
sense.
Because those are permanent hardware information. You know exactly what binary information you have to store. The number of ones and number of zeros in the information. So if you know that there are more zeros, less ones, then I'll go with this one. Less ones means I need less transistor, right? If I know that there are less zeros, more ones, then I'll go with this one. So that's why they came up with this student. So that you basically want to use one of these two options that will give you the design with the least number of transistors.
And isn't it with the space limitation also
Hmm?
for VDD, for applying VDD on the circuit?
Well, you see what is VDD and ground, these are the two supply reference. And same line can be used interchangeably as VDD or ground line depending on where you are connecting the source, where you are connecting the supply. So inside the IC, these are like identical line. So circuit overhead and complexity wise, number of transistor, number of connection, number of wires, both are same. But when you talk about overall system, in the system, if I have less number of ones, then I will go with this. If I have less number of zeros, I will go with this. Yes.
What about the size? The size of the
One good thing
N
about
MOSFET
this, yeah, you can
and the
always
P MOSFET.
minimum size transistor in this design because we are not worried about if you use very small transistor, it will take long time to make it a 0 to 1 and 1 to transition. But in memory design, we don't have any intention to make 0 to 1 and 1 to transition. Sense amplifier will see it is going upward or downward, it will amplify. So memory design always tries to use smallest possible. If it is in 18 nanometer, the width will be 18 nanometer, not more than that. So sometimes depending on the requirements you may use, but compared to logic design, memory circuit always uses smaller transistor, smaller size transistor because inside the core, it doesn't need to make a full 0 to 1 or 1 to 0 swing. Yes.
Would you ever select a slightly larger transistor in cases where you care more about resilience than speed?
Yes, definitely. That as you were basically for design requirement, even if you are talking about 20% transition upward and 20% transition downward, sense amplifier will kick in. For both that 20%, smaller transistor will take longer time. So there has to be, and then you say, depending on noise characterization, depending on power characterization, we have to play with the size. But comparatively, compared to logic circuit, inside that memory core, we can always use much smaller transistor. So then we concentrate on these two different ROM. ROM 1, MOSROM 1 and MOSROM 2. Now this is just one single binary. Now let us look at complex design. Two side by side. This one, the first one where one side of the transistor is connected to VD. Now as you can see, I'm using same line, green line, sometimes supplying VDD, sometimes supplying ground. It doesn't matter. So now, if I blindly follow this, then in parallel to every word line, I have to put a VDD. In parallel to every word line, I have to put a ground for this case. But in IC design, the most expensive, most scarce, the resource is the number of wire. Interconnecting wire as the most expensive and limited in number. When you have billions of transistors to connect and you have limited number of wire tracks, so you don't have the luxury to sacrifice one wire track after every word line for that VDD and ground. So it is a standard practice to sandwich one supply line or ground line in between two word line, and the next pair and the next pair. Because this transistor source and drain connection interchangeable. It takes the name of drain if it is connected to higher potential. It takes the name of the source if it is connected to the lower potential. So it interchangeable. So now, as you can see, this VDD, one side of each of these transistors, wherever needed, is connected to VDD, other side is connected to big line. Here in second option, one side of the transistor is connected to ground, the other side is connected to big line. This one is called OR wrong. This one is called NOR wrong. Why we'll talk about it in a bit. So basically then let us go back. MOS ROM 1 is called OR ROM. MOS ROM 2 is known as NOR ROM. First we will explain the naming later, but let us look at this design. What binary set of binary word in word line 3 is stored in this case? Anybody can tell? It's a 4-bit binary number 0000, because absence means at every intersection is one cell. There is no binary sequences are preserved word by word. So it's a binary bit sequence of 4 zeros, 0, 0, 0, and 0, right? And the second line, what is it storing? 0, 1, 0, 1. This one is 1, 0, 0, 1. This one is 0, 1, 0, 0, right? So if I give you any random binary sequence and I ask you to design an OR ROM, this is basically, the textbook made a mistake here. They should have placed bit line 3 here, bit line 0 where, so don't make it. Because bit line 3 always in binary, that is the most significant bit. That should be the leftmost. So the numbering and mapping remains same. I typically draw bit line here. This Reve books, the previous version, they made a mistake. I emailed them, but they didn't correct it. So it should, you start from here. Bit line 3, 2, 1, 0. Now let us look at this NOR ROM. First line, it is NOR ROM, MOS version 2. Absence means 1, presence means 0, right? Absence means 1, presence means 0. One side of each transistor, wherever present, connected to ground, other side is bit line. So the first one is 1, 0, 1, 1. Second one is 0, 1, 1, 0. Third one is 1, 0, 1, 0. Second one is 0, 1, 1, 1, 1. All ones. So you see, these are identical design, but they are storing different information. This is all zeros, these are all one. Why? Because as you can see, one side of the PMOS transistor through a permanently on switch PMOS transistor, it is connected to VDD. Here through an NMOS transistor with a bias on switch, it is permanently connected to ground. So I will take output from the top. Here I am taking output from the bottom. Sense amplifier and the output connection will be here. There, sense amplifier connection will be over there. So bit line will be our input output line. Word line will be activating the transistors. Now the question is, let's look at the naming. Why it is called OR and why it is called NOR. Inside every ROM array, if I just take F1 column, bit line 1 column, it is acting like an OR gate. All the transistors that are connected to bit line, the output, if I just take word line as the input, bit line as the output, it is acting like an OR gate. Here, every column, every bit line column acts like a NOR gate. Can I have the side pen? Let me explain why it is acting like an OR. So since every bit line is acting like a NOR, it is called NOR. So let me draw bit line column 3. So bit line column 3, first one there is nothing, second word line there is 1, third line there is 1, right? Sorry. Yeah. And then fourth one there is nothing. So this is our bit line. One side is connected to ground. These two together connected here. This is connected to ground. So this is connected to VDD. This is connected to VDD, right? This is bit line 3. And here, what I have? Word line 1 and word line 2, right? Word line 1 and 2. So now, what is an OR gate? Let's say word line 1 and word line 2, these are the input signal. For 1, 0 be 1, OR gate. For 1, for 0, 1, 1. For 1, 1, output will be 1. Only for 0, 0, output will be 0. That's the OR gate, right? 2 input OR gate. So now, if this word line is activated, that means it is 1. This transistor is on. VDD is connected to this one. It will produce a 1. Right? If it is 0, it is off, it doesn't matter, it is getting connected to VDD. Right? Now, if it is 0, if it is 1, this will be off, this will be on. Still it is getting connected to VDD, it will be 1. If I now apply third combination 1 and 1, both will be on, this will be charged, it will be 1. If I apply 0, 0, both will be off, it is default connected to 0, then it will be 0. So I am getting exactly column wise an OR type operation. That's why it is called OR long. Now let us draw the third column of the last column of the NOR. So it is, this side is default on PMOS, this is connected to VDD. Then I have my bit line here, bit line 3, and I have 2 transistors. Connected here, connected here. This is connected to ground, not VDD. This is connected to ground line, right? Middle node. And then this is word line 1, this is word line 2, right? Word line 1, word line 2. Middle, I just put correct. So here, what is a NOR? Word line 1, word line 2. Input combination can be 0, 0, 0, 1, 1, 0, 1, 1, right? For 0, 0,
1,
it should be 1. For 0, 1, it
0,
should be
0,
0,
0,
0,
0.
0. So for, it is default connected to VDD, right? So for 1, 1,
0,
it is 1, both of them are on, ground is connected, so you will see a downward, so it will produce a 0. Let's start from 0, 0. For 0, 0 here, both of them will be off, so it will produce default value of 1, right? For any other combination 0, 1, 1, 0, 1, 1, one of them will be on, ground will be connected, it will say downward, and it will produce 0. So every column is acting like a NOR gate. That's why it is called NOR ROM.
Sir, when both inputs are 0, like how it is producing 1?
Because default value is connected to VDD. So when I apply 0 and 0, both are transistor off, so this ground is not getting connection to bit line. So bit line value will stay at default high value VDD, so output will read 1. Bit line 3 will read 1. But for 0, 1 combination, this one will be on, ground will be connected, so bit line will be discharged. SAS amplifier will see that it is going down from its default value, so it will produce a 0. Similarly for 1, 0, 1, 1, ground will have connection to VDD, so in bit line it will go down and it will produce output 0. So that's why it is called NOR ROM. So in both OR and NOR ROM, implementation complexity will be exactly same. We have to run either ground line or power line between every pair, every alternate pair of quad line, and then we have to make sure that we have enough space for this connection to power or connection to ground, input connection and connection to bit line. You know that in VLSI, whenever you need to provide a contact, you have to spread the wire further away from each other so that those vertical contacts do not get shorted with each other. So area wise, you have to sacrifice a lot of area for those contacting dots. Complexity wise, and then you have to sacrifice at least for every 2 work line, 1 supply track or ground track. So it is expensive but very robust design. So then designer thought about, well, if I can have an OR, now you as the designer, again, which one you choose depending on bit sequence, depending on bit sequence. So if I tell you, I give you a binary bit sequence, 4x4 bit sequence or 5x5 bit sequence, then you look at the and ask you to implement the MOS-ROM circuit. Don't tell you OR and NOR. If I tell you that with minimum number of transistors, you make sure that you count the number of zeros and number of ones in the whole sequence and implement with the one that gives you minimum number of transistors. So always, so secret is select absence, like more ones. So you select the one that means absence of device is 1. So that's 1, right? More zeros, so absence gives 0, right? So that's how I remember. Now that's the end of this ROM design, 3 types. So you can take over. Yeah, any question?
So on your the OR ROM,
Yeah.
you had a voltage bias at the bottom. What was that for?
Oh, that is to turn on the transistor. So basically, we don't want to keep the So actually, I should have discussed. In the OR ROM and NOR ROM, we have shown 2 different ways of activating. In case of OR ROM, it is connected. PMOS transistors are connected to ground. In case of OR or NOR, it is connected to bias. These are the 2 different ways to turn on and off those ROM array. Let's remind me at the beginning of next class, I will discuss that.